So this is where we left off. We had just finished this problem, but I just want to make sure everybody understands kind of what's going on with this. So put all your phones away and click everything closed and all that stuff, please. Just give me a minute or two with this. So look what we got. We got two results here. We found that 27y minus 3z equals 0. And then we were able to combine two different equations and come up with the result that negative 9y plus z equals 0, right? How did we do this, right? Let's kind of think back to what our strategy was. Well, when we first picked these equations up here, we picked 1 and 3. We eliminated x in favor of y and z. We kept the y and z in there, right? We don't want to eliminate, when we eliminated the same variable in two other equations, what happened was we got the same equation, right? Everybody see that? If I divide this by 3, I get the same thing as this. So that didn't really tell me anything new, did it? Okay. So where would I go from here? Well, I need to see if I can eliminate the y and see how x relates to z now, right? When I picked two different equations and I got the same result, that's telling me that this is not a single isolated point, right? It's not one ordered triple. There's not a single solution. I'm going to get an infinite number of solutions, but I need some more information. So I want to pick, I don't have to pick different equations. Like I picked 1 and 3 here, and here I picked 1 and 2. But I need to eliminate a different variable. So what if we eliminated y instead of, we pick 1 and 2 and we eliminate y instead of x? What happens? Okay, let's try that. So if we pick this equation, to eliminate y, I could just multiply the middle one by 6, couldn't I? Everybody agree? Okay, so look what happens here then. We're going to leave this one the same, and we get 3x minus 6y plus z equals 0. And we'll multiply this guy by 6 and get 6x plus 6y equals 0. Okay, now if we add those up, this time the y's go away, and we end up with a 9x plus z equals 0. Okay, so now we got a connection. The z's did not go away in either one of these two cases, right? I was able to get the y's to drop out or the x's to drop out in the blue case, but the x's and the z's stayed here and the y's and the z's stayed here. So what's this telling me? It's telling me that I can compare x to z or y to z, but I can't get I can't get only one variable to remain in an equation ever. Okay, I can't get a specific ever. It never works in this case. That's okay. This is telling me that x is equal to negative 1/9 z, and y, if I use this equation, y is equal to positive 1/9 z, and z could be anything. So there's a kind of subtle dependence that's set up here, right? The value of z could be any real number, but depending on what the value of z is, that's going to determine the corresponding values of x and y. Say it again. Well, no. Well, so what that means is we're going to get a single line through three-dimensional space, right? Everybody get that? So like depending on the value of z, that's going to determine what these two values are. And if I string all those together, this ends up being a single line, which makes sense because this is the intersection of three planes that don't intersect at a point. They intersect on a common line this time. Okay? Everybody get that? Okay. What can you tell me about the three planes? are any of them, and we kind of did this work yesterday, are any of the planes parallel or the same? Not, they can't be parallel. Are any of them the same? First and third are, right? We know that because when we combine the first and third equations, we got 0 equals 0. So those are the same plane. So two of the planes overlap, and then we have a third different plane that's going to intersect the other double plane, right, in the form of a line. So our solution this time is a line that's described by these equations. So how would we input this into our answer? Okay, I don't know why that one's picked. That's not right. So it is not A. The answer is B. There are infinitely many solutions, but we have to write those solutions where Z is the free variable. That's the one that could be any real number. Okay, so this is the correct answer. What goes there? Well, the x coordinate is what in terms of Z? Negative 1/9 Z, right? So that's what goes there. Negative 1/9 Z. What goes there? Yeah, y is equal to positive 1/9 Z. And Z is anything. Z could be any real number. Okay? Doesn't that kind of make sense if you think about what a line means? Like, think about a line in 2 dimensions, right? Like if we have y equals 2x minus 7, well, x could be any possible real number, couldn't it? I can plug any value in for x, and that's going to determine the corresponding value of y. So we get an ordered pair that sits on the line. This is just analogous to that. Okay. So give me 1 to 5 on that. I mean, you might have to go back and look at this again. I get that, right? I mean, there's a lot going on there. Okay, the good news is these kinds of systems that are difficult to solve like this, well, all these systems, we're going to be able to solve more easily. I'm going to teach you guys some matrix methods, culminating in a technology trick that you can use with a matrix calculator. Well, where would you find a matrix calculator? Easy. They're on your TI-84s. So I'll show you the trick on the TI-84s. And there's now a Desmos matrix calculator that's really awesome that you can use also when you want to solve really big systems. And the advantage is not only can we solve 3x3 systems, we could do like a 10x10 system if we wanted to and solve that with a matrix. If you look at, where did I put this? I know this is kind of interesting. Where is that? Solving linear systems can get a little cumbersome. Here we go. Oh, that's not the one I wanted. Man, I can't find it. Well, gosh darn it, where did that go? Let me just Google this real quick. Oh, I know where I have it. Yeah, here it is. Okay, I had this in my notes somewhere. So why would technology be so useful? And I'm definitely something I'm going to show you guys. Here's why. To solve, and this is like even with matrices, like row operations you're going to learn about, those are essentially algebra steps. This is the number of, in the most efficient way possible, if you were to solve a linear system, this is the number of steps required, where n is the, if we're an n by n linear system. So if it's 3 by 3, n would be 3. Well, if we evaluate this expression, let's just do this in Desmos. Like if I just take this expression, let's enter a function here. So t of n is equal to 2/3 n cubed plus 3/2 n squared minus 7/6 n. And let's just set some values for n. Oh, why'd that not work? Let's make this, I guess I just do this, t of 3. So it takes 28 steps minimum to solve a 3 by 3 linear system. Okay, we've done it. I mean, that's not brutally difficult. We've done some stuff like that. I mean, we handled it. But what if you jump this up to like a 5 by 5 system? That's getting pretty big, right? 115 steps. What if you want to jump this up to a 10 by 10 system? Okay, that's a lot of time, right? You feel like spending time in doing 805 individual algebra steps to solve a system. We jump this up to a 25 by 25, that's going to take you a while, right? And what are the odds you're going to make a mistake? Probably pretty good. So it's useful to have some technological means of solving these big systems, and that's what a matrix, once you learn how to use matrices, that's what a matrix calculator lets you do, right? So this has enormous practical implication for like actually doing math, right? I mean, like when you want to really when you really want to be able to apply math to solve linear systems, which you do a ton. Like essentially, like knowing how to solve linear systems enables you, that you use that a ton in quantum mechanics. You'd use that a ton in statistical applications, right? In economics, things like that. You would be using a ton of this stuff. A lot of calculus-based, like differential equations problems, really depend on the ability to manipulate linear systems. So you will, if you go into a highly math-related field, which I hope you consider, you're going to do a lot of this stuff. Okay, you guys can make a choice. Do you want to talk about 4D stuff today, or you want to hold off on that? Hold off? How many people would rather just, how many people vote for a work day today to finish up with the work? Okay, I'll let you do that. Just why don't you work? I'll put the other assignment, if I haven't put both assignments up, I'll put them up. Yeah, that's fine.